Now let us see the problems. The last part are some problems here. What is this circuit? If you remember, I can't remember what kind of circuit is this one. It's half-wave rectifier. Because when it is positive, this positive and this negative, you have a current here. Because the capacitor will be short circuit, then the current is moving this direction and it will charge the capacitor and will move through the resistor. When this is the opposite, when this is positive, the other one is positive and this one is negative, then the diode is open, then you don't have a diode. And when you don't have a diode, so when this one is negative and this one is positive, the diode is open, then you will have only this circuit. And in this case, the capacitor will start discharge in the resistor. Then, of course, in this case, you have a signal like this, for example. If this is the signal supposed to be like this, half-wave rectifier, then the output will look like this. And so on, like this. Okay, so here, say for this circuit, determines the peak of the output voltage. So what's the peak? If the input voltage here is 12 volt for the very first the root mean square value. Okay, it's 12 volt. Okay, and R load, this R load is 50, and the capacitor is 1500 microfarad. Then in this case, what is the peak? We need to know what is the peak. The peak value is this value here, of course, this one. Okay, the signal is 12 volt root mean square. When you have a 12 volt root mean square value, so what is the peak of the input? The peak is 12 times square root of 2. Okay, because the root mean square, okay, if you want to calculate the peak from the root mean square, you multiply it by square root of 2. So this is the peak. Then this is the voltage or the peak voltage across the load or and the capacitor also. The output voltage will be 12 times square root of 2. Okay, but you have to subtract 0.7 volt because there is a voltage dropped on the inductor as well. There's a voltage dropped on the diode. There's a voltage dropped on the diode. Then the total voltage will be 12 times square root of 2 minus 0.7 volt, which is 16.27. So 12 times square root of 2. You can make it 10 to 2 to the power of 0.5. And then you subtract 0.7. It's 16.27. The second one, we have the voltage is 18 volt root mean square. So again, the voltage here is 18 times square root of 2. You can make it like this, power of 5, 0.5. Then the maximum here is 25, almost and half. Okay, so root mean square, you multiply by square root of 2. Then the voltage at the input, the peak value is 25.455 and so on. Okay, and this is a resistor, and this is a resistance and capacitance, and we need to find the output here. The output for this circuit, what we have for this circuit is the output is half of this voltage because you have a ground here. Ground is the middle. Okay, so you have to divide this voltage here by 2. You use only half of it. So you divide the input. The input was 25.45. You divide it by 2, then this is the voltage here between these points here. This voltage, this range here, from here to here. Okay, and then you subtract 0.7 volt, which is the voltage across the diode, then minus 0.7 volt, which is 12.0279 volt. So it's almost 12 volt. So this is the voltage across the or the across the resistor or the output voltage. So here, say determine the peak output voltage. So first we have 18 square root of 2 divided by 2, and then subtract 0.7 volt. Let's see what's next. And this circuit is full wave rectifier, of course. But as I remember, if you remember, I said that the problem in this one that you use only half of the voltage. As you can see here, we use only half of the voltage. But if you use a bridge like this one, we use the full wave. We use a full wave here. Okay, so if the voltage here is 18 root mean square, then it's 25. The peak is 25.45. Then this is the voltage, the peak voltage here. It's the input. Okay, but the only problem here is that the peak voltage will be what? Will be to this 25.45 minus what? Minus 1.4 volt, because this is we have a voltage dropped on 2 diodes. So use this one minus 2 times 0.7 volt. Okay, so it will be 1.4. So 25.45 minus 1.4, which is so again 25.45 minus 1.4, that is 24.05 volt. For the next one, this is a clipper. Remember, this is a clipper. When it is positive like this, then it will clip the positive part. And it will clip the positive part for what here? This V clip is what here? V clip is 8 volt. This 8 volt. Okay. And you have a 0.7 here across the diode. Then it will clip the voltage at 8.7 volt. 8 and 0.7, then it will be 8.7. So when it is positive, it will be clipped at 8.7 volt. So what's the question here? We need to find the output waveform and its amplitude for the circuit shown. Okay, so if this is 10, you see, it's moving like this. Okay, this doesn't look right. Okay, of course, this one here is 10. This is 10. Then 8.7 will be here somewhere, of course. Will not be will not be here. So maybe the drawing is not right. So 8.7 will be somewhere here. But anyway, it will be clipped. The concept is the same. It will be clipped at 8.7, and in the negative, it will not be clipped. It will be a full wave like this. So this is how it looks like. Here, the negative half and the positive half, there it is, look like this. It is clipped at 8.7. Okay, so this is a positive clipper. Let us see the next one. The next one is a dual clipper. It is clipped at positive and negative because you have 2 branches here. This one is, as I said, this 0.7 for the positive, 0.7, and the voltage here is what? 6 volt. So it will be clipped at 6.7, 6.7 here for the positive half, and for the negative half, this is 0.7 again, and the voltage here is what? 4 volt. 4 volt. Then it will be clipped at negative 4.7 in the negative half. So this is how the signal look like. It will be clipped at positive 6.7 and negative 4.7. Is this a question? Determine the output waveform? Yes. And its amplitude for this figure. Okay. So here, if this one is 12, so the maximum here is 12. But it will be clipped, the output will be clipped at 6.7 and negative 4.7. This circuit is a clamper. This one is a clamper because we have this capacitor here. Okay, so in this case, the input is 8 volt. So it will be clamped by 8. Okay, so it's supposed to be, if you have a 8 volt, supposed to be you add 8 volt in the third quarter, like as I explained before. In the third quarter, you add 8 volt, but you subtract 0.7 volt. So it should be clamped by 8 minus 0.7, which is 7.3 volt. Okay, 7.3 volt. But what? But we have a source here. Volt source. That's 2 volt. Okay, so it will not be clamped by 7.3. It will be clamped by 7.3 plus this 2 volt, which is 9.3. So everything will be you add a 2 volt here, and here you add a 9.3 volt. 9.3 volt. How again this 9.3? First, you're supposed to clamp it by 8 volt because this is a positive clamp. But because there is a voltage dropped on the diode, which is 0.7, you subtract this 0.7, which is 8 minus 0.7 will be 7.3. And because you have the source, voltage source here, you add this source. This is a DC power supply, just 2 volt. 2 volt plus 7.3 will be 9.3. So this is how the output look like for this clamper. Let's see what this one is. Just a bridge, of course. This is a bridge, and this is a transformer. It's transferring 110 volt root mean square, which is this is a regular power that we have, and to 11.6 volt root mean square. Of course, this is a root mean square. The peak of the sine wave, in this case, you just multiply this number by square root of 2. Then if it is 11.6, you multiply it by square root of 2, which is what? Let's see here. 11.6 times square root of 2 equal 16.4. Then the voltage here at the input is 16.4 volt. But because this is a full wave rectifier with a bridge, then you have a voltage dropped across 2 diodes, 0.7 and 0.7. Then you need to subtract 2.7, which is 1.4. So 2 times 0.7, not 2.7, 1.4. So 1 minus 1.4, then it will be 15 volt. Then the peak of the output here of this V will be 15 volt. 15 volt. This is what we have here, yes. So this is what we calculate here. And then what is required here? Design 15 volt AC to DC supply capable of drawing. Sorry. Oh, come on. What is this? Okay. This cell phone is working automatically. Okay, so now they says that it needs to draw a 200 milli. So you just, if you have the voltage here is 15 volt, you need the current to be 200 milli. Then if you want to calculate R load, use Ohm's law. R load equal the voltage divided by the current. The current is 200 milli, which is 0.2. 15 divided by 0.2 will be 75 ohm. So the resistance is 75 ohm. What else? Design a circuit that will limit its output signal voltage to a range of negative 5 volt to positive 5 volt. So this is clipper, of course. It's a negative 5 to positive 10. So this is a dual clipper. So if you want to make it 10 volt, okay, is this right? Okay, let's see. This one is supposed to be a little bit different. Let's make it, okay, let's correct this one. To make it 10 volt, you have to add this branch. This branch is right. Okay, but the voltage here is not right, is not accurate. Okay, this is supposed to be 9.3. 9.3 volt. Okay, practically it's like this. Ideally, it's supposed to be 10 volts. That's right. 10 volts, right. But if you want to make it practically, there is a voltage dropped on the diode. If it's silicon, 0.7 volts. So The total here will be 9.3 plus 0.7 will be 10 volt. That's it. And if you want to have negative 0.5, negative 5 volt, you need to add this branch, the second branch. And you change the diode direction. And this voltage is supposed to be what? 4.3 volt. Okay. So usually you need to consider the voltage across the diode. That's 0.7. So in this case, this 5. If you need 5 volt, then you have to add 4.7, 4.3, not 5. This will create the output like this. This is the required output. Okay. Let us see. I believe this is the last problem. This is a homework, and as I explained before, this signal, this circuit is a very important circuit that we use sometimes for telecommunication as a demodulation, amplitude demodulation. And it is a peak detector. Peak means it will detect the peak. So imagine that you have this signal here. So how the output look like? In the first half here, the diode is on. Then you are charging the capacitor. Okay. Then you will find the voltage here. The output will be like this one at this point here. And then when it start to decreasing like this, the capacitor will discharge. Then the voltage will decrease like this. Okay. And then after that, when the peak, when the voltage start to increasing again like this, then the voltage will increase. Then the capacitor will discharge. Then you increase the voltage. Then you discharge. Increase the voltage and discharge, and so on. So actually, the output will be almost, you are fitting the peaks like this. That's why I say this is a peak detector. So the output signal, as if it is exactly as if you are curve fitting the peaks, the peak points. Look at the peak points. You are curve fitting the peak points. So this is used when you need to restore these peaks. The peaks represent the original signal in telecommunication. When you send the signal, voice signal, for example, this is how the signal look like, this one here. But because if you want to send it, you can't send it because it has a very low frequency. So you need to upload it or carry it by a high frequency signal. This high frequency can travel in the space, in gigahertz, for example, high megahertz. Okay, so but your voice is just few kilohertz, or so it is. You can't send it in the space. So you need to carry it, exactly like when you have a baby and you want to move the baby from one place to another. You have to get some person, adult person, to carry him, exactly like this. So here at the end, the other side, you will receive this signal and you want to restore the original signal, your voice signal. So you have to do demodulation. So the demodulation will create the signal here, detect the peaks and restore the original signal. So in this case, the signal will look like what? Will maybe look like this, for example. Something like that. So it will not be exactly the same like the original one, of course, but it will be close to it. You will not feel the difference. You may feel some noise, of course, depending on the accuracy of this circuit and the frequency of the carrier. Same for this one also. This is almost a big detector also, the same like this. Ah, so this one is not. I missed some of them. Okay, so you just try to look at the peaks and curve fitting them. Ah, and so on. I'm drawing with the mouse, so that's why it's very hard. And sometimes PowerPoint is creating this line. I don't know why. So this is supposed to be going like this, and then returning back like this, and so on. So this is the output signal. So for this diode signal, draw the output signal for the input signal below, and explain the result. Why it is look like this? Because this is actually a half-wave rectifier. Then when the voltage is positive, you are charging the capacitor. When it is negative, it will discharge, and then it will return back when it is positive, and so on. So thank you very much for watching, and if you have any question, let me know in the live lecture, and see you in chapter 4. Goodbye.